and welcome to another Photonics Next Fall Summit session, Theoretical Spectral Modeling of Fluorescence Crosstalk and Filter Spectral Edge Position Jitter, sponsored by IDEX Health and Science and Semrock. I'm Justine Murphy, an editor with Laser Focus World and multimedia director of the digital infrastructure at Endeavor Business Media. We welcome your questions during today's session. Send them at any time by simply typing into the Ask a Question box on the side of the screen and hitting Submit. And we'll answer as many of those questions as possible during a Q&A session that will follow this main presentation. If you have any technical difficulties during today's event, just use that same Ask a Question box and our technical experts will be happy to help. And we recommend disabling any pop-up blocking software or extensions in your browser because sometimes these can cause issues with the webinar player. And please be aware that today's event is being recorded and you'll be notified by email when that's available. And now let's meet our speaker, Dr. Michael DeLay, a senior applications scientist at IDEX Health and Science Semrock. You can learn more about him in the speaker bio tab. Hello, Dr. DeLay. We're so happy to have you here. The floor is yours.
Thank you. Thanks, Justine. I'm going to share my screen. And then I will go ahead and put the presentation there. And we can get started. Okay, so So I'm talking today essentially about SearchLight. This is a modeling tool for use in fluorescent microscopy that was created originally by Semrock, now part of IDEX Health and Sciences. So I'm going to talk about how one sort of something basic about SearchLight in the first place, and then focus in on a couple of topics of interest. One of them sort of indicated below. One of them has to do with how you go about managing, or at least calculating, in situations where you have spectral crosstalk between channels. And then the second topic is to assess the effect of manufacturing or precision, or maybe lack of precision in the spectral edge position. So what we refer to as jitter. And out of that, we can arrive at a couple of conclusions. But first, let me start with looking a little bit at microscopy, and I will talk about microscopy from the context of these topics and related to SearchLight itself. So what we are talking about here is capture of fluorescent signals in a microscope setting. And the idea is that one derives from those signals, or from the images, one derives quantitative information on the presence, absence, concentration, etc., of different substances which are biologically or medically relevant. And these are usually taken from live cells or tissue. The instrument that is used here is typically a fluorescence microscope that might either be something one buys from a major microscope provider, or one designs and constructs something around a specific set of design principles, for example. And then one has samples, biological samples, which are prepared with suitable fluorescent agents. And they're either chemically bound to the substances at hand, so that they can then indicate the relevant parameters or numbers, or alternatively, it might be in solution that is dissolved in cases where these agents are reporting on the environment or characteristics thereof. Now, the microscope itself uses a light source, of course. Light is necessary for the fluorescence process, and that light must be passed to the sample under test, and that light will then excite the molecules of that fluorophore, the fluorescent agent. And then the fluorescence process results in light being emitted, and part of that is captured by that same microscope, and then it's sent off to a detector, which is either a camera, or it might be some kind of a photodiode or other point detector. So from the standpoint of SearchLight, we can start thinking about this by describing the fluorophore. That is sort of the starting point in any kind of analysis with SearchLight. And that's indicated in a graph here. This is a typical SearchLight type graph. It shows wavelength along the bottom, and then we have the spectra of these, the excitation on this side, the emission on this side, with a sort of characteristic, somewhat symmetric behavior around this area of the crossover point, and then the vertical axis just indicates some kind of arbitrary scale of intensity or brightness. Now, in order to bring the light to be able to affect this fluorescence or to excite it, one needs typically a microscope lens. And the reason why is because these regions of interest are usually quite small. And that means one has to demagnify the beam very significantly by, a factor, like as it says, about 10 to 100. And then the idea is that way you can intensely illuminate a small region and stimulate that response. So that lens, of course, then also captures part of the emitted light. And that emitted light then will proceed through the rest of the microscope in a magnified form so that it can be imaged onto, say, a camera detector or passed, again, to a point detector. So that means we have a single lens, and we now have to share it between this incoming excitation light, incoming from a light source, and then we also must share that with the emission light, which has to go to a camera or something like that, and that separation is performed by a dichroic mirror, and the word dichroic in this context means that it has it transmits over one range and reflects over another. And typically, in most microscopes, one runs across the dichroic reflects the shorter wavelength light, which is used for the excitation, and then transmits the longer wavelength light at the emission side. So now we can start introducing the concept of the filters. And that is because many light sources emit a wider range of wavelengths than is convenient or really even feasible. So, for example, an LED might pump out a fairly broad beam in a spectral sense, or one has, say, one of the older light sources which are continuous spectra and therefore much too wide for for this very specific use. And so we need an optical filter. And that filter would then pass only that light which you would say would efficiently stimulate the emission of the fluorescence. And then likewise, the emission beam needs an optical filter because there's a whole variety of light that's not desired, which could otherwise enter the system and then interfere with detecting the fluorescence. I mean, the point is in part that the fluorescence is not, it's reasonably bright, but it is not so bright that it can, it will not be diluted or contrast reduced by different sorts of undesirable light. So that is essentially the orientation towards the microscope, and that can be diagrammed in this way with a light source, an excitation filter, a dichroic, an objective lens, a sample. The emitted light then goes past the dichroic through an emission filter to a detector. From the SearchLight point of view, we can now overlay this display of the fluorophores, excitation and emission respectively, with the excitation filter spectral profile and the emission filter spectral profile in dashed and solid lines respectively, and then a dotted line indicates the dichroic, its spectral position in between to help reflect one, that is the low wavelength light, and transmit the long wavelength light. Now in this case, we now have this vertical axis has some meaning. This 100 here refers to transmission in this case when you're talking about an optical filter, so this shows about 90% transmission. And the same for the dichroic and the emission filter. Now, of course, a filter doesn't just transmit, it also has to eliminate or prevent light from passing. It has to, in other words, block light from passing. And that is the essential purpose, because otherwise you can't obtain the proper behavior in the fluorescence signal. So that is then in SearchLight context, you can switch the vertical axis to show optical density. Each of these represents a factor of 10 of reduction of the light intensity. And one sees now, instead of a straight line like what I saw before, we see a slightly curved line has a certain with optical densities capable of blocking down to 7, or what we call OD7. And this blocking is accomplished by reflection, not by absorption. So that is a characteristic of the dichroic filter, the dielectric filters, excuse me, that are used in this situation. So at its most basic level, then, SearchLight allows one to plot spectral characteristics of these filters, the excitation spectra, etc. And all of these can be chosen from a catalog, which comes with SearchLight, which includes a wide library of all kinds of fluorophores, cameras, detectors, light sources, etc. And of course, you can also add custom data. So in this case, we have excitation and emission again, spectra in the green. We have a light source spectrum. This is an LED, most likely. And then here we have the spectral responsivity of a camera. So the way SearchLight, SearchLight, of course, has this ability to calculate, and that is separate from what we've been talking about heretofore, which is mostly related to just display. So the way this is implemented, it's described in a white paper that you can lay your hands on. And essentially, you start off by defining essentially arrays of parameters, which have to do with the spectrum of the light source, the spectrum of the excitation filter for all the other pieces. And then one can, using the algorithm here, one can then calculate the amount of light that reaches the detector. And this is the basis of SearchLight, and that's what allows one to do these sort of adapt the questions that one asks for looking at crosstalk, optimizing filter parameters such as spectral edge, and in general to look for rational ways to choose filters, especially in situations which can be challenging, let's say. So here's an example of SearchLight in action. So this is the page that shows what SearchLight would look like. Here's the spectral display that we've seen. And then over here, one finds a small bar panel, which is shown again here and larger, and that's the calculator. And there's a number of, you can have any number of these. And into each of these, you put a number of, you put in your filter set or the filters that you're going to be using. One provides the fluorophore name and those characteristics that are needed, that are pulled out of the database, similar with a light source and a detector. Then on the side, one has a number of outputs. So this is the calculated signal level at the detector for this combination of circumstances. There is the fluorescence signal. There's a noise that I will describe in a moment. There's a model for autofluorescence that can be used. And then out of this, one can define a signal to noise ratio, which is the ratio of this signal divided by the sum of these two. So as an example, we can look at the case of 3 different filter sets for fluorescein isothiocyanate, FITC. And there are 3 cases. We have one set that's offered has so-called brightest signal. The other one has the brightest contrast, and then there's one that's intermediate. So if one then sets up with this one being, let's say, the one that one normalizes those signals to, then one can see that in contrast to this middle set, the one set has a lot brighter signal, higher signal, but less signal to noise. And this one is the converse, that is lower signal, but higher signal to noise. And this relates to essentially in this case, the width of the pass bands. Wider pass bands tend to collect more signal. Narrow pass bands collect less signal, but it's more selective and there's less chance of noise entering. I have to talk about the noise here. The excitation light noise that we're talking about is essentially the light that is reflected from the preparation through the microscope, past the emission filter, and to the detector. The situation is that There can, for example, be 4, 5, 6% light reflected from the preparation simply because the preparation itself is reflective, and that light, of course, doesn't change its wavelength. It's not fluorescent, but it still can get past the emission filter because we're talking, as I mentioned before, only about, say, 10 to the minus 7 transmission level, which is corresponding to OD7, but still, that's enough light to interfere with fluorescence. That gives you an idea that fluorescence is, in a way, can be a rather small parameter. So the other kind of example would be for looking at crosstalk. Crosstalk is an example shown here where one has, for example, a green channel, and here in the red channel one finds a lot of light present, and then when it makes an overlay, one can see that there's a lot of yellow, which means that these are pixels that share the green and the red together. So there's a bleed through, which means essentially in this case that green is contributing to the red, and so we're not really getting a good image of the red channel at all. If one then uses the proper methods to control crosstalk and bleed through, then one can see a much better separation, like in here. So the crosstalk and bleed through arise from this little area here. So here, for example, we have a couple of different filters. There's FITC, and then the other one, TRITC, which is in pink. And here is the filter set for the FITC, which is one of the ones we talked about before. And then this is the same filter set, but now one has the presence of this fluorophore at the same time. And it can be excited by the same light that comes through this light channel can excite this pink excitation area, and the emission will then follow, and that will have a little corner which comes in, which is able to reach into gets past the filter and then contributes essentially what is called crosstalk. An analogous situation over here. Again, there's a certain amount of excitation of the wrong channel, which then bleeds into the TRITC signal. And the way one does this in SearchLight is you put in all your filters and then simply choose, just adjust the fluorophore. You can change the fluorophore from one that is the expected one to the one that is not expected for the bleed through, and then you can see the amount of contribution that the wrong fluorophore has to the desired fluorophore. If one has, for example, a whole set of Alexa fluor probes like this, then one can make sort of a chart which shows the signal source and then how much each crosstalk source contributes, and one can get an idea that, for example, down here there's about a 30% crosstalk taking place, which Alexa fluor 700 contributes into the Alexa fluor 647 channel using those particular filters. So let me then move to the remaining topic here, which is the two sort of aspects of interest for this particular talk that I thought might be interesting. One of them is a situation in which we have the crosstalk. There is some crosstalk present, and let's suppose a significant amount. And the usual approach in this kind of a case is to use some kind of spectral compensation method. So that means one acquires the individual signals independently, and then one assumes that there's an algebraic summation. So it's a factor of, for the first one, another factor for the second spectrum, and you add those together in some combination to get to achieve the spectral result that is observed. And then from the numbers that you derive, you can then after the fact in future experiments, then extract the signal from the signal plus crosstalk. There's, of course, uncertainties, and that can, in this procedure, and that can lead to larger uncertainties in signal levels. So another option that one can consider, at least, is to move the filters away from the overlap area, expecting, of course, that you would get a lower signal level. But on the other hand, it may reduce the crosstalk more than the signal. So that's something one can simulate in order to sort of look for possibly a better solution. So here is a case at hand. Here's a case of a fluorophore called ROX. That's the blue channel, and then ATO 590, which is the dun colored one. They overlap very significantly. The ROX channel uses the blue exciter emitter. I'm not showing the dichroics here. And the ATO 590 shows the magenta ones. So there's a lot of overlap. And so now one can see whether one can find a different strategy. So here's one, not necessarily the best. This is just perhaps a starting point. But to illustrate the point, we now move the filters away from the excitation and emission peaks. So there isn't, even though the spectra are, of course, exactly the same of the fluorophores, the filters are at different locations, so one expects a different kind of behavior. This particular exciter is not really optimal for the situation, but it was to some extent forced by a lack of availability of an LED that could be somewhere, let's say, to the red. That would have been somewhat better. However, pursuing this approach just as a sort of a way to think about it, one can make up a chart that shows the high signal, high crosstalk case that has one has good a good signal level. This is times 10 to the -7 in these kinds of units of watts at a pixel. Then there's the signal and light noise. That is the signal to noise ratio. This light noise refers to the reflected light, as I said before. And these are good values. But the signal to crosstalk level is not especially good. It's about 2 to 1 or a bit better than 2 to 1. So that's not really all that great a result. It might put a lot of stress on one's spectral subtraction process, for example. If one uses this admittedly not optimal option of moving the filters to a different place, one can find, at least for this one, a decent level of signal and of signal to noise. These are certainly workable. But now the signal to crosstalk levels have increased quite a bit. So the last one I will talk about is the issue of critical edges. So in a fluorophore situation, one has an excitation and emission filter, and these two edges are called critical. They're critical because if they move laterally during deviations from manufacturing, you'd expect that would have some significant effect on the amount of signal. So that's what we're going to check with SearchLight and see what might happen. So here's a case where we have a Sci5 filter set using the bright line, which is the sort of standard filter set that Semrock supplies for this. And what I've done is I've shifted the emission filter to the red by about a nominal amount. And now I'm comparing that to use of the Avant filter. So the Avant filter sets are different in the sense that they have a very steep blocking. They achieve much more blocking out here to prevent the light from being reflected into the detector. And they also use precise edge placement to minimize or significantly reduce anyway the position jitter of this critical edge. So now one can simulate this in SearchLight and get some kind of an idea. What one sees is that the bright line signal is reduced by 12%, which is quite a significant amount, whereas the Avant is only reduced by 3%. The Avant signal is in any case bigger. So I think the take-home message here is that if you increase the precision of control inherent in the manufacturing of these critical edges, you can get quite a bit better consistency in the numbers you get out in terms of if you look at multiple machines. In other words, if you think of multiple devices doing the same job, let's say measuring the spectra and calculating the numbers that that one gets for the fluorescence intensities, then one can see that you would expect much better consistency if you're using the Avant type filter sets rather than the bright line, just due to the kind of differences that you get from difference in manufacturing. So that's my presentation. I will return to stop sharing and come back to your questions.
Great. Thank you so much, Dr. DeLay. And let's move into that Q&A. As I mentioned earlier, if you'd like to submit a question, just use that Ask a Question box. And we do have some in here already, so let's just jump right in. Can SearchLight be used to model more complex fluorescence microscopes that have more than the minimum number of optical filters?
Yeah, so this is not necessarily spectacularly easy, but the way I have done this in the past is by essentially combining parts that are less variable, essentially convolving these elements together, and then adjusting the ones that leaves one free to adjust the, let's say, one filter that is the most critical. In this kind of a situation, one can more or less go about something like this. This does not work for a huge number of elements, but if you're dealing with, say, 3 or 4, then it becomes feasible.
Okay. Is the reduced spectral edge position variability of precise edge placement achieved by a more careful selection of filters?
That, yeah, so that careful selection of filters would imply that what we're doing is, let's say, only providing those filters that actually have this spectral edge characteristic. And I would say that what we're doing is really a little different. What we're doing is we're doing much more careful control of the coating process in that case. So the idea is you only make the good filters. You don't have to throw away all the bad filters,
okay,
so to speak.
All right. And how can I download the SearchLight white paper? Where can we find that?
Let's see. So let me share my screen again. Bring this back. Okay, I lost my presentation. So
I think the audience can see it.
Yeah, if they're able to see this, let me make it a bit bigger.
Okay.
If you photograph this QR code, then I think you'll be able to download the white paper directly.
Okay, great. Well, it looks like we are just about out of time. Any questions that we weren't able to get to today will be addressed directly later via email. And once we're done here, a quick survey will pop up. Please do fill that out because your input will help guide future content for these events. And stay tuned for our next session, which will begin right after we're done here, specifying F-theta lens for high power and short pulse lasers with Christian Dennert, an electrical engineer with Couriertronics Sil Optics. And with that, I would like to again thank Dr. DeLay for this really interesting presentation, IDEX Health and Science and Semrock for sponsoring this session, and of course, all of you too for joining us.
Thank you.